Continuing on from the last video, we're going to be taking a more detailed look at some other learning rate schedules that we can use. A lot of these learning rate schedules are going to come from recent research. And given that the last video that we saw setting the learning rate is very important, we also find the same for learning rate schedules. And having a good learning rate schedule is very important for fast convergence of models and then the ultimate performance that we're going to get from the model. So we're going to split the video into two parts. The first part, we're going to look at the different shapes that we can use as part of learning rate schedules. And then in the second part, we're going to look at how we can modify these shapes, use them together, maybe repeat the shapes, and see how we can come up with a more comprehensive schedule that has lots of other different features. So let's start with the different shapes. So the previous video, we looked at a few different simple shapes we can use. The first thing we looked at was the factor schedulers. So this is where we had stepwise decay. We'd maintain the same learning rate for a number of iterations, and then we'd drop by a factor. So some of the more recent research has suggested that having a smoother learning rate schedule is better than having jumps in the schedule. This came about from looking at how to train MXNet in under an hour. And what was found was having a warm-up in the learning rate helped improve the convergence of the model. And a warm-up is where you have a lower learning rate at the start of your schedule and then it increases after that. The different techniques you could have for warm-up, one would be having the stepped increase, and another one is having that smooth linear increase. And it was found that the smooth linear increase was better for convergence than having a big step. So it's seen quite often that having a smooth shape for your learning schedule is more preferable than having the steps. So that's where some of these ideas come in. So the first shape that we're going to be taking a look at is called the triangular shape. And more specifically, we could look at different variants, the slanted triangular. So this was originally proposed by Leslie Smith in the Cyclical Learning Rates for Training Neural Networks paper in 2015. And then the slanted variant was introduced by Jeremy Howard in 2018. So what does this schedule look like? Well, it's very simple, looks like a triangle. So we're moving from a lower bound of the learning rate to an upper bound and then back down to the lower bound. And so that gives you the triangular shape. We've got a linear increase to begin with from the lower bound to the upper bound, and then we have a linear decrease from the upper bound to the lower bound. Here we can see we have actually got a slanted triangular shape, and we can control that by changing the increase fraction. The increase fraction determines the proportion of the iterations where we're going to be having an increase in the learning rate compared to the decrease. And here we've got 0.2 because 20% of the iterations in our cycle are going to be for the increase. And so the way we specify the length of the cycle, here for this implementation, specify the cycle length. So we want this triangular cycle to be defined across 1,000 iterations, meaning that we're going to have 200 increasing and 800 iterations decreasing. So let's just change the increasing fraction, maybe to 0.5. Now we can see we have a symmetric triangle, and this was the original triangular schedule that was proposed. We also have control over the minimum learning rate and the maximum learning rate too, so we can change the magnitude that we're dealing with for different learning rates. So these are custom implementations, and we'll take a look at how we have implemented these learning rate schedules later, but they can be used as a drop-in replacement for the MXNet LR scheduler default schedules that you could use. So we can just implement these and then add them to the model. And in the last video we saw how we can use the learning rate schedules as part of training. The key thing is we pass the schedule to the optimizer through the LR scheduler parameter, and we could just use this as a drop-in. And then as we train on neural networks and we take trainer steps in Gluon, automatically be using the schedule for us, which is really nice. So this would be an implementation of our triangular schedule. To initialize our schedule, we take in the parameters that we've already discussed, And then for our cool, because remember we're implementing a class which is going to be callable for a specific iteration. Our domain is then split depending on whether we're increasing or in the decreasing part of the cycle. So that's where these if conditions come in. And then we've just got the formulas for the linear interpolation of the learning rate between the two. After the cycle has completed, you'll actually notice that the lower bound of the learning rate is what it continues on as. So here we're at 1 because that was the minimum learning rate. So now another shape that we could look at, and actually we've seen this in the previous video, is the cosine shape. This was proposed in stochastic gradient descent with warm restarts in 2016, and it would look something like follows. We have a nice smooth shape between the upper bound of our learning rate, that's defined as the max learning rate, and the lower bound, which is minimum learning rate. And it does look like a cosine shape because we've got a shallow gradient at the start, we reach a peak in the change of the learning rate, and then we tail off at the end. And similar to the triangular schedule, we maintain the minimum learning rate after the cycle length. So again, we have got the cycle length defined as 1,000 iterations, and beyond that, it's going to maintain minimum learning rate. How we implement this, we again take the arguments for initialization, and then we use those when we call. So for a specific iteration, we will process that iteration with the formula for working out where we should be on the cosine curve. We make adjustments based on the cycle length and then the minimum and maximum, find the range, and then we return the adjusted learning rate. In this instance, the variable is called adjusted cycle. And if not, we just return the minimum learning rate if we're past the cycle length. And so that's just how we would implement the cosine annealing schedule. So they were some interesting shapes. It's unlikely you'll be using them on their own. You'd want to modify them in certain ways, and certain papers have suggested how you could use different shapes in combinations, have repeating cycles, have warm-ups and cool-downs, etc. So we'd want to combine all this to create your learning rate strategy that's going to help training models quickly and get to a good performance. We call them modifiers here because the implementations adjust other learning rate schedules. So we could drop in a stepwise decay, which is the multi-factor scheduler, and make these modifications on top of that schedule. So it's not a whole new schedule, it's just making adjustments. And we'll see how that comes into play later on. So one of the first modifications we can make to a learning rate schedule is to add warm-up. And warm-up was a technique that was used in the paper Training ImageNet in 1 hour in 2017. And this helped for convergence of models when using very large batch sizes. So a large batch size is good because you can train quickly, but it has effects on how the model converges. And so if you were just using stepwise decay, which you'd get from the multi-factor scheduler in MXNet, it was found it didn't converge particularly well with batch sizes greater than 1,000. But one thing that did help is that instead of starting your learning rate high and just decaying, at the very start you should have a low learning rate and then increase to the highest learning rate and then follow your normal learning rate strategy down. So this is an idea that we can add to our existing schedules as well. It was found that a linear warm-up was better than having a stepped warm-up, so that's the version that we've gone for here. And if we look at it graphically, this is adding warm-up to the multi-factor scheduler. So we've seen this multi-factor scheduler before. We're using the same steps as the previous video as well. We do 250, 750 and 900 steps. They're the iterations at which we want to take the steps, and we're halving the learning rate. So we have initialized our scheduler, set the base learning rate to 1, and now we add warm-up. So linear warm-up here has been implemented in such a way that it takes another schedule and just adds the linear warm-up component to it. So we have beyond 250 epochs here would be just the normal schedule, but up to 250 we have this added warm-up part. And the way we've done that is you pass the schedule, you specify where you want to start the learning rate. In this case it's 0, so on the far left hand side we see that we start at 0 for the first epoch, or first iteration, sorry. And then across 250 iterations we have the linear warm-up, which has got the linear line up until 1. And so this is something we can add to all the other schedules as well. Just in this case we've gone for the one proposed in the paper. As for the implementation, here we can pass the schedule when we're initializing, and we then use that when we call the schedule. So this acts again like a callable class where we pass a single iteration and then we return the learning rate. And inside of this function we are actually calling the underlying schedule that we passed through originally. So this is going to call the multi-factor scheduler in the example previously. But before we get the length of the linear warm-up, we're just going to do that linear interpolation between the starting and the finishing learning rate. And the finishing learning rate will be the first learning rate of the schedule. So if we look back at the graph, we don't define the final learning rate of the warm-up because we already know it. The final part of the learning rate of the linear warm-up is going to be the first learning rate from our original schedule. So that's all worked out in the implementation, and it just adds this nice linear warm-up. Then we've got the same idea just applied at the end. So this I've called cooldown, and graphically you'd see a similar thing. We have this linear interpolation between the final learning rate and then the specified finish learning rate. So we create our multi-factor scheduler as before, set the base learning rate to 1, and then we let this schedule run for 1,000 epochs. And that's defined here by the start index of our linear cooldown. So we have passed the multi-factor scheduler to linear cooldown. We say we want to start the cooldown at 1,000 iterations, and over the period of 500 more iterations we want to move down until we get to the finish learning rate. So here we've got a drop from just under 0.2 down to 0, or down to 0.001, sorry, because that's what we've specified in the linear cooldown. So very, very similar to what we had for the warm-up, just at the end. And after 1,500 iterations, we'd get the same thing where we just stay with the finished learning rate. This would then continue out. Implementation looks very, very similar. We're just working out where we should start the cooldown, and that's defined in the initialization. And then we're going to work out which segment we're in, whether we should be sticking with the normal schedule as defined, or whether we should be doing the cooldown, which is defined here. And if we're finished with the cooldown, let's just continue with the finished learning rate. Okay, so now let's bring these ideas together and define the exact policy that was presented in the Leslie Smith paper in 2017. And this was used for superconvergence. So superconvergence is an effect that can be found for specific cases, and in the paper they used it for training CIFAR 10. And they find that if you use a specific learning rate schedule, what they call the one cycle schedule, you can train CIFAR 10 really, really quickly and get the same level of accuracy as you would have done with a more traditional schedule. So what does the schedule look like? Well, it's a single cycle of the triangular policy that we saw earlier on in the video, followed by a period of cooldown, and that was the last technique that we saw. So we've implemented both of these things before, so it should be quite easy to bring it all together and create what we call the one cycle schedule. We can create our own one cycle schedule after we've implemented it, and we pass the required parameters for this. We need to define what learning rate we want to start with, which will be the start learning rate. So we start at 0.1. We move up to the maximum learning rate of 0.5. and back down to 0.1, and that's the triangular part. And we do this across the cycle length number of iterations. So it takes us 500 iterations to do that. Then after we've done the triangular part, we want to do the cooldown component. So we have a cooldown period defined here as 750 iterations, and we want to drop down to a learning rate of 0.001, which you'll find here. And beyond that, we continue out the same value. So we can use these, adjust the values as required. The parameters I've used here aren't the same ones used for CFAR 10 in the paper, so you'll need to reference the paper to find the specifics for that one. An implementation is really simple because we've implemented all these subcomponents separately. We do some error checking up front when we initialize the schedule, but ultimately what we want to do here is create the triangular schedule to begin with various min-max learning rates and cycle lengths. And then as before, we pass the schedule to the modifier, which is the linear cooldown, and we add some linear cooldown. And these two combined, we can then just cool the schedule directly. Because again, this is a coolable class where we provide the iteration and expect back the learning rate for that particular iteration. And this will give us the one cycle schedule. The last modification that we're going to look at is having cyclical learning rates. So this is from a paper that we've referenced before when we were looking at the triangular schedules, but it was the central idea of the paper to have these repeating cycles in your learning rate schedule. So here is an example of what a cyclical learning rate schedule could look like with the triangular shaped waves. Why would you want to have cycles? Well, the intuition behind the idea is to be able to move from different areas of the loss surface for every cycle. So some people have used this idea to create quick ensemble methods. So every time the learning rate goes back down to its minimum point, you'd expect that to be a point with the best performance or the lowest loss of your model. So you could create an ensemble of models at each lowest point across your cyclical learning rate strategy. But having the ability to increase the learning rate quite high brings noise into your training process, which acts some form of regularization. And so that's why in first results it looked like cyclical learning rate strategies were a good idea. More recent research has suggested that just having one cycle seems to be sufficient for fast training, but the idea originally was having repeating cycles to having the fully cyclical learning rate schedule. So the different parameters that we can control when having the cycle, we've obviously got the minimum bound and the upper bound defined by min LR and max LR. Here we're going from 0.5 to 2 and cycling between the two. And then we've got the cycle length, which is essentially the wavelength of our cycle. So it's set to 500 iterations here, which means we're going to go up and down every 500 iterations. Or we can control that. So let's just make an adjustment. If we go to 1000, we're going to double the wavelength or decrease the frequency, and we're going to have less frequent cycles. Once again, the parameters I've used here aren't directly taken from the paper, but this is the form of the learning rate schedule you should be using if you want to replicate the results in that paper. You'll notice there's one key difference between this modifier and the previous one we've looked at with warm up and cool down. So in those examples, you created an instance of a schedule and then modified it to add the cooldown or the warm-up. But here, because we have to control the frequency of the cycles, we don't pass in an instance of a schedule. Instead, we just provide the class. So within the cyclical schedule, we can create the right learning rate schedule shapes in which to cycle. So that's why we pass the class in rather than a specific shape. So now if we look at the implementation, we can see how that's done. And when we saw the minimum and maximum learning rates set in the example before, they were being passed as keyword arguments. So they were being passed to the schedule class when that was being used. So the core parameters for the cyclical schedule are the class of the schedule we want to use. In the example, it was the triangular schedule. The cycle length was how often we want to repeat the shapes. The cycle length decay, so these are a few different features that I've added for specific cases. So cycle length decay, that is where we want to increase the wavelength as we progress through the training. And so the idea there was in a paper that we'll see next, and so that's useful there. And we can also decay the magnitude of the cycles as well. Both of these by default are set to 1, and that's why in the example before we didn't see these. But both of them are used later on when we do the call of this class. And then the keyword arguments are some of the more configurable options for the schedule class. So if we pass the triangular schedule, for example, some of the arguments for triangular schedule include the minimum learning rate and the maximum learning rate, and both of those are passed when we create an instance of the schedule class. So if we now move down to the call method, we'll first of all work out which cycle we should be in, because this is a repeating shape. Maybe 1,000 iterations down, we might be in the 5th cycle, so that's one component. And then we use that to work out the decay. Potentially we want to be reducing the learning rate over time. And we create our schedule further down, and this is where we pass the keyword arguments. So the min and max learning rates will be passed when we create an instance of the triangular schedule. And then we use that and make some more adjustments. So this is the paper that I was referring to, where we had a varying cycle length over time, and it's the paper called Stochastic Gradient Descent with Warm Restarts in 2016. So this is adding a few extra modifications. We're using a different shape to before. Instead of triangular, we're using the cosine annealing schedule. We specify some of those parameters that will be passed as keyword arguments to cosine annealing. We need to specify the minimum learning rate and the maximum learning rate. This is just for the first cycle. We specify, as before, our initial cycle length, which is 250 iterations. So for our first cycle, we'll see that it goes from 2 down to 0, or 0.01 more specifically, across 250 iterations. Then for the next cycle, we have a few different modifiers, and these were the ones I was talking about before. So the first modification is the fact that we've specified cycle length decay is 2. So this is actually, instead of a decay, because we've got a number greater than 1, this is going to be leading to an increase in cycle length. And it's actually going to double the cycle length every cycle that we take. So for the first cycle, we had 250 iterations. For the second cycle, we've got double that. So the second cycle is going to take 500 iterations. And that's going to lead us to having being on iteration 750. And then the cycle after that will have a cycle length of 1,000, and this continues. The other modification we get for each cycle is to have a decay. And so here we've set the cycle magnitude of decay, and we can set that to 0.5. So that means the magnitude of the learning rate is going to be halved every cycle that we take. And now we can see that for the fact that we move down in the second cycle from 1 to 0.01. And I think that would be halved as well, so it would be 0.05. And this, was the cycle that was proposed in the paper. And again, the specific parameters are different in the paper, but you can use this form of learning rate schedule to replicate some of the results in the paper. So that completes our review of learning rate schedules. Check out the description for links to the code that's been presented here, and give them a try while training your own networks. Thanks.